An important topic in engineering statics is vectors. Sometimes engineering statics, the class or the study, the discipline is actually called vector mechanics. And that's because vectors play such an important role. So what is a vector? So vector mathematics is really essential to the study of statics. And that's why I want to do a little review today. And that's why most textbooks start with an introduction to vectors and vector math. A lot of what statics is about is representing forces as vectors and then making sure those forces balance out so that something doesn't move. So a vector is usually represented by an arrow. And so it has a tail end, and it has a tip end. And then it has some length, and the length is representative of the magnitude. And then it also has direction, which is really represented by the orientation of the tip to tail, or another way to think about it would be the arrowhead. So one thing that's unique in statics is that the direction is usually split into two characterizations. One is the sense, and that's really the orientation of this tip to tail. So that means that in this case the tip is oriented kind of to the upper right as opposed to the lower left. And then the other part of the direction is called the line of action. So what we normally think of as direction is actually split into these two components. One being the sense, which is really designated by the arrowhead or this tip to tail orientation, and the line of action, which would be kind of an imaginary line that passes collinear along the same line as that vector. So our vectors have both magnitude and direction. That's really the key to representing a vector. But a vector is kind of a mathematical quantity. So in engineering, the question is, why do I care? Why is that useful? So vectors in engineering are going to represent a physical quantity, like forces. We know, for example, that F is equal to ma. And here I've drawn a little arrowhead over the force and the acceleration, and that is how I represent a vector. Force is a vector, force vector. This would be my acceleration vector, and my mass is not a vector, which means it's a scalar, and so it has only magnitude and no direction. Suppose I have a mass, and my mass is 10 kilograms, 10 kg. And if I were to apply a force to the right, say I apply a 1 Newton force to the right, then by my equation, F equals ma, and I want to figure out how much that little mass is going to be accelerated as a result of pushing it with that force. So I have to divide the force by the mass. So this is 10 kilograms divided by 1. Oops, I did that wrong. Let's fix that. So it's force. The force is 1 Newton, and a Newton is actually a kilogram times a meter per second squared, divided by the mass is 10 kilograms. So this is going to be 0.1 meters per second squared. Here, now this is a vector. So I have to show the direction. So it's going to be to the right. So it's accelerated to the right because the force vector was to the right. So it's going to have the same line of action and the same sense. The acceleration vector is gonna match that. Okay, let's look at a second example. So let's suppose I have a bigger mass, we'll call it capital M, and it's 100 kilograms. And I push to the left by 1 Newton. So now my numbers are going to change a little bit. So now acceleration is going to be force divided by mass, capital M. 1 Newton is 1 kilogram meter per second squared, divided by 100 kilograms. And so this gives me 0.01. And what are my units? My units are meters per second squared. And again, acceleration is a vector. So the direction is going to match the direction of the force. And in this case, it's the resultant force. There's only one. If I had multiple force vectors acting on that mass, then I could boil it down to one resultant or one effective force. And so the resulting acceleration is going to be a result of the resultant force. Okay, so the direction then is to the left to match that 1 Newton force on my capital M. All right, so this is our acceleration. And this, intuitively, if we just take a moment to compare the two, if we compare these two results, considering the magnitude specifically, when I have a smaller mass and the same force, so in the first example I looked at 10 kilograms and a 1 Newton force, and so it's going to be accelerated 0.1 meters per second. If I have a larger mass, 100 kilograms, and I apply the same force, it's going to be accelerated much less. So mass is actually a measure of inertia, which is resistance to motion, and that's going to be important in the study of dynamics. But since we're talking about statics today, I want to wrap up this discussion of vectors with really the key point to statics. And the key point in statics is that in statics, we want the acceleration to be 0. We don't want things to move. So I want to build a bridge or a building, and I want everything to balance out. That is, I want all of the forces to balance. So if I have a mass, whatever it is, and I have a variety of forces acting on that mass, maybe this is 1 Newton, and then I had 1 Newton to the left. I could have 10 newtons acting upwards, and then maybe I have other forces. The whole point of statics is that when I add up all of these forces, here I'm showing 5 forces, it could be any number. I want that sum, so F equals ma, I want that to be 0. I don't want it to move. So the whole point of statics is really to make sure that a mass does not move. The first part of statics is really going to be focused on making sure the sum of forces is equal to 0. What this deals with is translation. So motion in a straight line, or if you're dealing with a particle, it's not going to rotate. But then when you have to deal with rotation, we're going to introduce something called moments. And we want the sum of moments to be 0. And that is sort of our other form of motion. So we want 0 translation and 0 rotation. So the whole point of statics is to keep things from moving. We want the acceleration to be 0. And vectors are a key part of that analysis.